Hey all, this is Dr. B again. This is a video to show you another part of NCBI. There's layers to this, of course. And what I'm going to do here is actually search for a protein and not a nucleotide. So you see here that I went over and I chose BLASTP. And I grabbed a gene identifier here, actually a protein identifier for the Huntington protein. This is one of the ones that was in your NCBI database trial you did. So I want to do a couple other things. So what else, and by the way, a great thing about NCBI is if you're ever unsure where you're supposed to put somewhere, you literally just click on this little thing and it'll tell you exactly what it needs there. So there's a bunch of different ways. Like I could have put the amino acid sequence, I chose the accession number. The query subrange, from here I can look at one particular area to look for residues, so that's nice. I also, if I have this in a file, like a text file or something, I don't have to just put this in here. I can upload, especially if it's like a really long nucleotide sequence, you can do that. Job title, you can call it kind of whatever you want. And if you are going to align two or more sequences, and if you click this button, you notice that it'll open up another tab for you to be able to put that in there. So it's a good way for you to be able to also align sequences. But we're not doing that right now. So a couple other things. As far as databases, that's why NCBI is so good, because you can use a whole bunch of them. So if I go down to here, one of the ones I'm going to teach you about later is something called Uniprot. But I can decide which particular database I want to use to look for it. Uniprot's a very common one. Protein Data Bank is another common one. And so you can just leave it generic right now, or you can make it more specific. If you also know the organism, in other words, you don't want a gigantic list of all of the other versions of this protein that's found in a lot of other organisms. You know that you want to look for Homo sapien or E. coli, etc. That's a really great tool. Other things, of course, this is kind of showing which algorithm we're using. And this one is going to be BLASTP. And I'm going to be covering some of the other blasts as well. But one other neat thing is this algorithm parameters here with the plus sign. So if I click on this, I actually get a lot more things that I can search for. And you will notice, by the way, that there is a Blossom 62 here, which is the default matrix, and there's a bunch of different PAMs. So this goes really well with the last video I made, kind of having an understanding of, the relative idea of either evolutionary relationship and or the relative number of mutations. And this existence 11 extension, or 11 extension, is the gap cost. Don't need to worry about that. And then from here we can just hit blast. And I'm going to pause the video because it's going to take probably about a minute or two to go ahead and get the results. And I'm glad I paused the video. It took about a minute and a half, 2 minutes. So here is what we get. And we can see here that this particular protein has a lot of relationship and a lot of identity from a lot of different organisms, which is really nice. So here's a couple other little tidbits before I get into some of this area over here, especially e-values and whatnot. So first of all, if you always wonder, like, what is this? What is Gallus gallus, the scientific name? The beauty is all you have to do is click on it. And it'll tell you what it is, and you can see that, oh, that's a chicken. And so again, there's other taxonomic information here as well. So what we see here is that the way I would interpret this, first of all, we have 100% query covers all the way down, and that basically tells us that it covers the amount of the query to 100% at least, which is nice. Now you can see here that our particular query is similar to 99.48% to this particular Gallus gallus protein. And so, which, by the way, this is the Huntington protein. So let's go ahead and just compare a couple of them. Let's compare this one, which had the highest score, and let's go down to like here. And let's go to, I don't know, let's randomly grab that one. And so now if we hit an alignment of these things, as a pairwise alignment, this is the first one, And so we can see here that we have 99% identity, so which is nice. Excuse me, you can see exactly where there's a bit of a difference. And then as far as the gaps, there's 16 of them. So we can see here that the query right here that we put in is shorter than the subject. And so this thing has a 16 base pair area that we don't have, at least in ours. And so that's also important, because when we talk about domains, the question is that an important area of domain? Typically domains and proteins are conserved. So this is nice. You know, you can do a comparison this way. There's a bunch of other things that you can do with this, which is really cool. So let me go first to graphic summary, and you'll see here that there's only 3 lines. And basically now if I were to get rid of let me go back to the descriptions and do the select all. If I hit graphic summary now, you'll see this gigantic list. And basically each of these is one of the subjects. Now if I click on it, that was the very first one, you see that it's all red. And that red is good. The higher the alignment, the better conserved they are through conservation of each of the alignments. Or in other words, they're basically the same, which is really, really cool. And so to see that alignment, you can also click here and then just hit alignment, and it'll choose that same thing that we just saw, and you can look at it that way. And so this is a really great thing for you to just kind of pal around with and see what you get. So what I just did here is I clicked a graphical interface here, and let's see how long this takes. I might be pausing the video again. So this sequence viewer kind of gives us a more specific look at things we might want to look for in here from another graphical view. So what we can do is, if we just want to look at certain areas, like you can see right now that the full view of these two is the same. But I can choose, let's just say I want to look between 900 and 1100. And you'll see what happened. It took this area and magnified that area down here. And so I can see all kinds of different alignments to what these are. I can look at the FASTA records, the GenBank records, all kinds of stuff. I can even look for a particular sequence. If I wanted to even get more specific, let me do that. This is down to the amino acid level. So let's just say you were at something like this and you're like, you know what? I know there's a sequence that I'm looking for in there. So let me just randomly just pick let's just go DKWKRL, and if I do that and I hit sequence, oh, look at that, there is one. It's from 1555 to 1560. And there it is right there. That's the one I just copied. But my point is, if you were in the larger zone of looking at the entire protein and you put that in there, it would let you know exactly where that was. So that's also nice as well. Couple more things. Let's go back to the descriptions part and get a little more specifics about some of the scoring things we have here. So again, max score is basically the highest score that has been done in the alignments. And so if you talk about how we were doing all of our scoring with Blossom 62, whatever the default was on that, that's the maximum score for this particular item. That's one of the reasons that's at the top of the list. That differs slightly from the total score, which is the sum of the alignment scores of all of the segments from the same subject sequence. Query cover we covered, and now we move on to the E-value. And the E-value is basically, it's a statistical relationship based on the numbers of hits that you would expect to see by chance. And so that's why the lower the E-value, the better. And because these are identical in one sense, they're very, very close related, the E-value is 0. Now the E-values can differ a lot. So now let me show you an example of how an E-value would differ and how we would interpret that. So I just put in about a 24 base pair DNA sequence, and it's specific to Ehrlichia ewingii, which is a tick-borne pathogen that's found in the Lone Star tick. And as you can see here, the great news is that it's clearly from Ehrlichia ewingii because we have a query cover of 100% identity, and the E-value is extremely small. And you'll notice here the max score is only 50. And the reason why, again, is that we only had 17 residues or something like that. I forget, it's like 15 or maybe 20 residues. So that's nice. But then all of a sudden you can see what's happening here is that the E value is starting to go up. And the reason why is because it's not as perfectly aligned. And so let's just do a comparison of our query with this one. And then let's do this one. And then let's do 61. Wow, that's pretty far. Let's do that one. And so if we do alignments of these, here's basically the first one. So we had 25 residues, that's fine. And we can see here that 100% identity, and that's really great, and that makes that E value really low. And then as we go down, this one's a little bit shorter. And we see that in this case, we have not the entire query covered. Part of the reason that the expected value went down is it's too small. It doesn't cover the entire area of it. So if we were to take a look at yet another one, let's go down to, let's just do, all right, actually, I tell you what, I want to change to a higher amount of these. Well, anyway, let me go to graphical summary first real quick. I'll do a select all. It's going to show you something else, but I can do that in a later video. So what you'll notice here is that there doesn't appear to be a lot of the red ones. And again, that makes sense because remember what our highest alignment score was. It was like 50 something. So that's why we're in the range of this. And why were the other ones above 200? Because the number of amino acids in the first part of the video was way longer than 200. And so when you have more and more amino acids or more and more residues, by the way, that's how I can distinguish using the word nucleotide from amino acid. It's just they're both a residue. The more residues, the higher the score. And so we can see here which ones these are and how these first four do represent the 100% alignment. And then I like this also because these shows where these things have a query covered. They're not all covered. And therefore, if the alignment scores are lower, that's where your graphical information is. So it's a really nice graphical way that if you were to line all these up, how do they look and where are some of them truncated? For example, this one right here is missing the 5' end of this residue sequence. So hopefully that helped. And this should be a good help for you guys. Let me just do one more quick thing. Let me go ahead and now, you know what? I'm going to save taxonomy for later. That'll be it.